Hello guys, welcome to my channel, and in this video I'll explain you article number 2.12, the parallel plate capacitor. As we have seen in the previous video that what a capacitor is, it is a device in which we store energy. It is arrangement of two conductor. Okay, so we'll see a parallel plate capacitor. Okay, obviously in this there will be two conducting plates. Okay, parallel, which will be placed parallel to each other. So let's start. I read the NCERT for you and explain it line by line. A parallel plate capacitor consists of two large plain parallel conducting plates separated by a small distance. Okay, in this there will be two large plate having large area which will be placed close to each other. There will be two conducting plates. Okay, so now we first take the intervening medium between the plates to be vacuum. So we'll start with vacuum, then we will fill another dielectric in that, and we'll see that how the capacitance is affected by the introduction of another dielectric. But first we'll start with the vacuum is in between the two plates. Okay, the effect of a dielectric medium between the plates is discussed in the next section. Let A be the area of each plate and small d the separation between them. Okay, so the area of the two plates is capital A. They both have the same area, and the distance between the separation between them is small t. Okay, so now the two plates have charges q1 minus 2, just as we seen in the previous video that the two plates, this will have plus q charge and this will have minus q charge. Okay, and the surface charge density of this will be sigma. Okay, and this is minus sigma. Okay, now since small d is much smaller than the linear dimension of the plates, we can use the result on electric field by infinite plane sheet of uniform surface density. Okay, if you recall from the first chapter, if there are two infinite sheet of charges having surface charge density plus sigma and surface charge density, the other plate having surface charge density minus sigma, then what is the electric field between the two sheets? That was given by E is equal to sigma upon 2 not 2 epsilon, epsilon only. Okay, so this was the electric field between the two infinite sheet of charge. But here the sheets are not infinite, they have a finite size. Okay, then still we can apply that result, because for a point, for the sheet having very small distance between them, the separation between them small, that is d square, very smaller than a, we can apply the result. Not at the edges but at the center we can apply the result. We can treat the sheet as infinite for the points inside the middle of the region. Okay, so now as we can use the result of electric field by infinite sheet charge density. Plate 1 has surface charge density sigma is equal to q by a, and plate 2 have surface charge density minus sigma. Okay, we know what is surface charge density. Sigma is surface charge per unit area. Okay, how much charge the plate has in a unit area. Okay, so now the electric field in different region is, okay, so we'll do the same thing as we did in the first chapter. So we'll find the electric field at 3 points. Okay, you see the electric field at this point. The electric field due to this first sheet will be in this direction. Okay, due to the second sheet this will be in this direction. Okay, since the surface charge density are equal in magnitude, okay, then what happens? There is the electric field get cancelled out, so there is no electric field. Similarly here you see the electric field is here due to second, due to first it is in opposite direction, it cancel out. But in this region the electric field due to the first conductor is in this direction and in the second is in this direction, so the electric field due to the both will be this. Okay, so for the first region, that is the outer region, the electric field due to the first conductor is sigma upon 2 epsilon naught, to the second conductor this is sigma upon 2 epsilon naught, because they are in the opposite direction, so the net electric field will be 0 in the first region. Similarly for the second region, the net electric field will be 0. But for the third region, that is inside the conductor or inner region of the plates, the electric field will be the sum of these two electric field due to the two charge plates, and this will be on adding, this will be sigma upon epsilon naught. Okay, and what is sigma? Sigma is q by a. Okay, so this is the electric field and in the region inside the two plates. Okay, the direction of electric field is from positive to the negative plate. Okay, and what is the direction of electric field? Obviously it is from positive to negative plate. Okay, now next Thus the electric field is localized between the two plates and is uniform throughout. Okay, so it is uniform throughout, the electric field is uniform throughout, and it does not depend on the distance. Okay, so it is uniform all throughout, the value is constant, like value of electric field is constant all throughout the region in between the plates. For plate with finite area, this will not be true near the outer boundaries of the plate. As I already told you, this result will be only true if we consider, because this result was for infinite sheet of charge, but in our case it is finite sheet. So, and in this only the region that is on the in between region, in the middle region, this result will be true. We can treat the two sheets as infinite sheet for that region, but on the region outside the, or the near the edges, the result will not be true. Okay, the field lines bend outward at the edges, an effect called fringing of the field. Okay, so near the edges what will happen, the field line will bend like this. Okay, the field line will bend like this, and this is called fringing of the field. So it is not constant near the edges. Okay, it is not uniform there. By the same token, sigma will not be strictly uniform and on the entire plate. E and sigma relative equation. Okay, however, for d square very less than a, this effect can be ignored in the regions sufficiently far from the edges, and the field there is given by equation 2.41 for the regions away from the edges. And for this condition we can take the electric field uniform, and the electric field between the plates will be this. Okay, so now for uniform electric field, potential difference simply the electric field times the distance between the plates. Okay, you know what is electric field? Electric field is simply the negative gradient of potential from this electric field. For a uniform electric, this will be potential difference is V and the distance between them is D. So this will be, so what will the potential difference? Potential difference will be E times D. Okay, now the value of electric field is from above, this is Q upon epsilon naught A. I put the value of this and times D. Okay, so now we'll find, this is the potential between the two plates, potential difference between the two plates. And now I'll find the capacitance. And what is capacitance? Q by V. Q by V is the capacitance. And when I put the value of potential here, so what I get when I put the value of this, so this will be what? I'll just simply put here Q upon Q D epsilon naught A. So Q cancel out, and what will get the value of C is epsilon naught A by T. Okay, so this is the value of, this is the expression for a capacitance between capacitance of a parallel plate capacitor. Okay, so now as you can see, the capacitance depends on the distance. Okay, if I keep the area of cross section constant, the area of the plate constant, then capacitance will be inversely proportional to the distance. So if I increase the distance, okay, then capacitance will decrease. If I decrease the distance, capacitance will increase. Okay, and similarly if I keep the distance fixed and increase the area, okay, then in that case area will directly proportional to area, and on increasing area of the plates, capacitance will be increased, or area decreasing the area of the plates, capacitance will decrease, which as expected depends on the geometry of the system. You can see it depends on the distance between them, and the area of the plates, it depends on the geometry of the system. For typical values like A is equal to 1 meter square, D is equal to 1 millimeter. Okay, when I put this unity, the area 1 meter square, then what I get the expression of C. So I'll get the value of C as 8.85 into 10 to the minus 9 farad. Okay, so this is the capacitance of a two plates of area 1 meter square placed at a separation of 1 millimeter. Okay, this much capacitance. Okay, this shows that 1F is too big a unit in practice, as remarked earlier. Another way of seeing the bigness of 1F is calculate the area of the plates needed to have C is equal to 1F, or a separation of say 1 centimeter. Okay, so you see the capacitance here for 1 meter plate, 1 meter square area plate, this is much. So we can just imagine how much will be the 1 farad capacitance. So we'll try to work out how much area of plate we will need to have a 1 farad capacitance. So we'll just put the C is 1. When I put C is equal to 1F, then using the same formula, what I get, so now the separation I put as again 1 millimeter square. Okay, 1 millimeter is the separation. Okay, 1 centimeter, I'll put the separation even 1 centimeter. Okay, from the same relation, and epsilon naught value we know 8.85 10 to the power minus 11. What will get the area of the plates? 10 to the power 9 millimeter square. Okay, so you can just imagine, if we want to have 1 farad capacitance, what we need to do, we have to have plates of area 30 kilometer in length and breadth. Okay, we need to have this much of plate area, 10 to the power 9 meter square, or which can be extended to 30 kilometer length and breadth. Okay, and they are separated only 1 centimeter, then we'll get 1 farad. So you can imagine 1 farad is a very very big unit. This is the reason we use smaller units of capacitance in practically, that is picofarad, microfarad. Okay, so I hope this paragraph was clear to you. In the next paragraph we'll discuss effect of dielectric on capacitance. Okay, so if you like this video, give it a thumbs up, so that my videos got recommended to who want to watch this kind of videos. Okay, do subscribe and share my videos. Okay, thanks for watching.